Hello everyone, how are you? I am Manu, this is Tommy. We work at LambdaClass. LambdaClass is a company based in Argentina. Also we have offices in Spain, Barcelona, and Uruguay, in Montevideo. Lambda is a company that works on difficult problems related to distributed systems, compilers, also cryptography and machine learning. And now we are entering in the video game industry. So we are creating a game studio, and we are here to show you our backend for supporting a lot of types of different games. So in this talk, we are going to talk about the games we are developing, also why we choose Elixir as a language, our architecture, like the server architecture and the internal architecture, also the main flow of one of those games, a little bit of code, how we debug the backend, and we are going to show you some metrics, some fresh metrics. So let's start talking about Cars of Mira. Cars of Mira is our first game. It's a fast-paced mobile brawler game where 10 players will fight each other, and the goal is to be the last one standing, okay? So here you can see two scenes, like the character selection page and the main scene. We have four characters implemented so far, and we are working on 3 more to release 3 more in the next few weeks. The other game is Champions of Mira. It's an idle RPG auto battler, where the idea is to create the strongest team as you can and fight in many modes like campaign or PvP or PvE. As you can see, these 2 games are very different, but they share 2 things: the lore and the backend that we are building in Elixir. So maybe you are wondering, why Elixir?
So, as you know, choosing a language is not the easiest choice. And also in the game development area, you have already the well-established framework of Unity, right? So our main, I wouldn't say competitor, because we are not building an engine, we're just building a backend. But one of our main choices was between Unity and Elixir. So we kind of divided this in pros and cons into 3 axes. The first one was easiness of use. Unity is the clear winner here, because there's such a big community, there's tutorials for everything, there's already a fully fledged 3D engine. But that's not all to it. We also wanted flexibility. And the idea is that C# is not our favorite language, to say the least. And it's also a scripting language to use in Unity. You can use it different ways in other places, but in there it's just a scripting language. And we wanted to build a whole ecosystem of games here, not just a single game. So in here, building something from the ground up is somewhere where Elixir wins. Also, Elixir is one of our main languages in all of our other projects, so it was a kind of nice choice for that. And then there's cost of operations. Deploying in Unity is very expensive. I don't know if any of you had to choose that. And this is very similar to Chris's talk for Flame. Unity is a cloud server, and they charge you for every single thing that you do. They charge you for bandwidth, they charge you for the amount of simultaneously connected players, they charge you for bandwidth. Did I already say bandwidth? Yeah. So they charge you very, very expensively. And we are very used to building Elixir applications and deploying them in bare metal servers. So it's something that we are very used to, and it's also very cheap. It's very scalable. Concurrency management is great. So that's, if we take these 2 things, we are definitely going forward with Elixir. So let's talk a little bit about our infrastructure needs. One of the particularities, like if you notice, we chose 2 games that were completely different, because if we started building the backend before thinking about the games, we would probably overgeneralize. And one of the things that we noted with these 2 games as an example is that they have very separate needs. Curse of Mira is a live game, it's multiplayer, it's very fast, it's not Call of Duty or it's not Counter-Strike, it's not an FPS, but you still need a very low ping, so you need servers distributed all over the world. We have 3 servers right now, one in Europe, one in Brazil, for instance, and I forgot to, like this morning we were playtesting and I forgot to change from Brazil, we're from Argentina, and I forgot to change from Brazil to Europe, and the ping was like very notable. So Curse of Mira has those needs. On the other hand, we have an auto-battler, which doesn't have any live capabilities at all. It's more oriented to single player, so it can be centralized. And also, you have other features like matchmaking that don't have these really live necessities. And I think there's an old saying that says, if you don't need to distribute, just don't. Like, distributing is always bad unless you absolutely need it. So what we did is we separated what needed to be decentralized and what didn't need to into an umbrella application. And this is just a general list, I will go through this very quickly, of the applications in which we divided these needs to be able to deploy them separately. I think what I will want to notice is that dotted line between matchmaking and arena, that's the most important thing of the graph, which is not obvious. And then all that is left to that line is deployed in centralized servers, and the arena is something that's deployed separately, because that's what needs to be close to the users. So let's just go quickly through each of these apps. As you may remember, I don't know, how many of you are familiar with umbrella apps? Okay, nice. Almost all of you. Unexpected. I mean, we're at ElixirConf, right? But still. So most of these are just modules. They allow for independent deployment. So eventually, we might take one of these and deploy them separately. For instance, if at some point, for instance, the game model, I'll talk about that in a minute, has needs that doesn't right now. But for now, all of these can be centralized. The gateway is our router that routes requests to each of the games. Then we have champions. We have both of these games as controllers, Champions of Mira and Curse of Mira, just Champions and Curse for the friends. And they handle the logic that is specific for each of the games. Then we have the game model, which is basically our persistence module. This holds everything like user data, player data, for instance, if you have a specific set of armor or swords, or your level, or your preferences, like for instance, if you, and what kind, your rank, that kind of stuff. So this is basically our database. And we also have the matchmaking service. This is also in the centralized server. And this is what lets you join people that are close to you, and also people that are your same rank. And this is something that's only needed for now in Curse of Mira. It's not something that we need for champions. And as you can see, then there is the arena. The arena is not persistent. It's where the actual game of Curse of Mira, where the battles happen, and that is, on the one hand, deployed separately, and on the other hand, it doesn't persist any of the state. It's completely ephemeral, and when the battle ends, then eventually that is reported to the game model. But during the battle, there's nothing being persisted anywhere. So that's also something that makes it very easy to distribute.
Yeah.
All right.
I'm sorry, I'm losing my mic, so let me know if you can hear me well. Here you have, from here, we are mostly going to talk about Curse of Mira. You can see here a little spoiler of what the game we recorded yesterday. We are playing here there with Uma. So
yeah, this is just our devs playing with each other.
we are pretty proud.
Yeah.
So
that's a danger zone that closes in, like Fortnite. That kind of mechanic.
So we won. Yeah.
We all won. Thanks for coming to the talk.
So before starting with the main flow, we want to show or explain you our internal architecture. So the green shape is the Shen server. Oh, come on. It's a Shen server, which is the source of truth, right? We have also processes that are the front-end client representation, but inside the server, the light blue ones. And at least we have the front-end clients, like mobile clients, web browser clients, or whatever. Oh. So For those front-end clients, those front-end clients cannot communicate directly with the Gen server, but they must do it with the representation via WebSocket inside the server, right? Then those processes can communicate with the Gen server directly via messages. So can you, sorry. Because I'm losing. Sorry. So let's talk a little bit about the entire cursor mirror flow. When a client wants to play, it only needs to click one button, play, okay? Then they will join to a lobby inside the Matchmaking Gen server, okay? Then the Matchmaking Gen server will wait for other players, and when inside the lobby, the Gen server had 10 players, or the first player had waited for 10 seconds, it will start an Arena Gen server. Okay? The Arena Gen server will return the game ID. That game ID will be used by the clients to open another WebSocket, but with the Arena handler process. Okay? So, in order to communicate with the game and send events and receive updates. It's important to see that we have two separate Gen servers. One for the matchmaking that handles all players, and other for the Arena. And we have one Gen server per game. Okay? So let's go a little deeper in what's happening during the matchmaking. As we mentioned earlier, each player will have their own front-end client, right? And will communicate with a handler process via WebSocket, and the clients can send only two types of messages: join or leave, okay? During the matchmaking. On the other hand, the Matchmaking Gen server will communicate the game ID to each client, okay? And that's it. It's very simple, right? So the Matchmaking Gen server, inside the Gen server, the flow is also very simple. The Matchmaking Gen server will receive the join request until enough players are there, and we check it every 300 milliseconds. And in any case, a new game or arena will start, and its ID will be returned to the client. As you can see, it's a very simple flow, and we want to show you each of our messages. We have three messages inside the Gen server, the Matchmaking Gen server. The join message, we save the timestamp when the next game will start. We save that in the state, in the Gen server state. The client is added to the queue, see, and we are managing only a single lobby. So all of the clients are in the same lobby, but it's pretty simple to change it to support different levels, for example. Okay. The second message is the launch game message. We check every 300 milliseconds if we need to start the game or not. Okay. If any of those conditions is true, we start the game. The last message is the starting game. The start game. We start the game. For starting a game, we take the first 10 players in the lobby and send it to the Arena Gen server. Okay? The Arena Gen server returns us the game ID, and we communicate that ID to each client in order to leave the lobby and enter to the game. Okay? After that, a game will start with the flow that we told you before, but we are going to go deeper now.
Yeah, so let's talk a little bit about the arena. So the game workflow is very similar to what we already seen. This is a repeating pattern in our architecture. We basically have the dumb clients that only can request stuff, and then we have the WebSocket, which have handlers containing them, and then we have their messages going to the game gen server, which is the arena, and then state being constantly updated through the WebSockets to the clients. One thing worth noting is that we use PubSub here, and the reason we use PubSub is because we have a single topic for each of the games. In that way, each of the handlers can subscribe to the correct game, and they can receive the updates that correspond to theirs and not to other games. So let's continue with the sequence diagram. This is just a sum of what Manu said a couple of minutes ago, but basically a client joins and then is notified that the game is starting. And then what is more interesting here is that the client communicates with its handler through a WebSocket. It requests either to move or to attack, and then the request is passed on to the arena. These dotted lines are not instant, they are not returns like we would have in a regular function call. You will see this in the code in a couple of seconds, but the arena constantly and periodically updates the clients with the current state. So let's see this handle call, like line by line. So this is how the arena reacts to a player moving. So let me take the pointer. I don't know if I'll need it, but yeah. Here, so this is just a regular handle call that we have a player identified by its ID requesting to move in a direction in a timestamp. And what we do is, if you can see, here's the state of the gen server, and the state of the gen server basically holds all of the state of a single game. So what we do is we simply get, using the map library, the player from the state, and then we used our player library to move it. This is less obvious than it looks. Moving it doesn't mean changing the position, it means changing the direction, and that will become important in the next slide. So what we do afterwards is we just update the game state, we look for the corresponding player in the players list, we update it, and we also update the timestamp. The timestamp is not so important for this talk, it's more important for clients so they can do corrections on their end, because they can be aware of what is the last event from them that the server processed. So we won't be getting into that, but we can talk about it more in depth if you want to after the talk. And basically what happens is at the end, the game updates the state. But so, as we said, this only changes the direction of the player, which will become important now. So this is something that happens every 30 milliseconds, as you can guess, because this is a handle info, and there's also this ticker pattern where you see the send after and the game tick rate milliseconds. Basically, there's a lot of things in the game that depends on the passage of time and not in particular players' actions. Those are most of the things in this list, like reducing player cooldowns, moving projectiles. Those are things that once triggered, they just move on their own. And also these move players, this is the odd one out, right? Because weren't we moving players in the previous one? Well, actually not. What we are doing here is using the direction that was updated by the player and applying the position. If you think about it, the reason being that with this, the player cannot hack their client and tell you, hey, I want to be in this position in the next second, and they can no clip or appear in any place. With this, the client only can tell you, I want to move in that direction, which kind of makes sense, right? Like, you have your body, you tell it, hey, I want to move in this direction, the world kind of lets you or doesn't let you. You can't just no clip through walls or stuff like that. So this is very similar, and this also it's our own anti-hacking system, very basic. We don't need more than this for now. Yeah. And then after doing all of this very, very advanced stuff, it's just a pipe. Then we just broadcast the game for each of the WebSockets. And this broadcast function that we have is just a PubSub broadcast to this game ID as a topic. Finally, we update the game state, and we apply that to the local gen server. So now we updated our clients and the local state in our gen server. This is just a quick note on our modules. We have two modules with business logic. One is player and one is a skill. Player just handles health, cooldowns, checks for skill usage. This is just a module configuration. And skill just sees, actually applies the attacks. The only reason why we are mentioning this is because of this specific node, which is that we don't apply skills instantly. Anyone that's in game dev, in live game dev probably had this same issue, which is animations and attacks need to match. So for instance, if Muflus is our main character, if you have that guy like swinging the axe, but the damage was applied before the axe landed, you probably lose a lot of immersion and also playability. So we basically have a threshold that determines how long is an animation, and the skill application is delayed using that threshold. And as we have the timestamps, then we can do that processing in the server as well, and we don't need to do it client side. So again, server is smart, clients are dumb, and that is important because they cannot hack our server, not this way at least. And back to Manu.
Debugging the backend. We are not going to debug the backend right here, but
hopefully, yeah.
We find we need to test every feature we develop, right? Right? So we found it quite challenging to test the functionalities we developed in the backend because of two reasons. We had to wait the front-end tip to deploy the developed in the front-end, or we had to struggle with Unity, and we don't want that. So we developed and we are maintaining a web browser client. It's a very beautiful browser client. You can choose any character you want, and you can play it. So, look, it's beautiful. The green shapes are colliders. The black shapes are players. You can see a difference between the size. The white circle is an ultimate, a Baltimore ultimate. The little red circles are projectiles, and they are fighting. They are really fighting. So this is what we use as backend developers to test our developments, because here we can see the hitbox, the real shapes, and it's very difficult to debug in the. Do you remember the video? It's very difficult because you have a camera. So we really love this.
Yeah, this makes the development iteration very short as well, because this is just like localhost, right? You can just spin up the server, play it instantly. You don't need to talk to the front-end team, wait a couple of days, get something like an application built, because you also need to wait for them to deploy the equivalent for the front-end, and they may or may not be up to date with what you're doing. So this allows us to have a very ugly, very quick iteration. And
do you like it? Yeah?
Please say yes.
Okay.
So let's benchmark a little bit. This is something that we did, I think, yesterday afternoon. So this is fresh out of the oven. I don't know if that's a phrase, but basically we are testing this in an ARM Neoverse server. We have two servers for benchmarking, one for running the server and one for running all of the clients. This is a very important thing, because if we had everything in the same server, you're not really testing bandwidth. So this is basically what we used to test was 9,000 bots doing random moves and attacks. And we had 900 games with 10 players each. So basically what you just saw, but multiplied by 900. And this is the state of our server according to HTOP. So it's at 96, 95% of occupation per core. It's not in red, that's good. And we need to see if this is working. So what we did was, outside of the servers not crashing, an application not crashing, which is just like the basic check we wanted to do, we also wanted a sanity check of how does this impact playability.
I'm sorry, let me emphasize, 9,000 clients, it's a lot.
Yeah, for a live game, right? Because if we are like just managing like a REST API, it wouldn't be very impressive, but with a live game, a little bit more. So this is what we did. We actually joined a game and tried to play it in this context. So basically we chose Muflus, because you need to choose Muflus, of course. And we joined a single game to see what the bots were up to. Like they were supposed to doing moves and attacks. That's an important part, because if we thought they were doing, but they were actually idle and they weren't sending messages, that would be a problem. So here's our character joining some random bots and seeing if they are doing stuff. And they are just moving and attacking in random directions. And the game is actually playable. It doesn't seem to have any lag or impact. So we were very happy with that benchmark. So
Yay.
Yeah. So basically, we're thank you. Thank you so much. A very small note on this is that our first setup had this same idea of 5 more minutes. Thank you. So we had one single server for the server, one for the clients, but we had a limitation of 1 gigabit of bandwidth, and we realized that we needed at least 4. So we were having a lot of trouble diagnosing why players were bots weren't joining, and we thought it was an Elixir limitation. It generally isn't. So it was we were being cheap. We need more bandwidth. All right. But how do we go further? What do we do next? Because we don't only want 9,000, we want more, and we are kind of at the limit of CPU. So some of the ideas that we're thinking about testing out is sending diffs instead of the full state. Currently, this benchmark that you saw, the game server is sending the full state of the game to all of the bots. So that's why it requires such a big amount of bandwidth. So we're thinking about sending the diffs, such as the same way that LiveView does when they send the updates back to you. We chose 30 milliseconds as an arbitrary amount of time for the updates, but we need to play a little bit more around with that to see how big we can make it before it stops being playable. And we also can test with other protocols. Right now we are using protobuf over TCP. We may play with Quick. But that's something that we always say, and yeah, we need to actually test it and see if it is better or if the bottlenecks are somewhere else.
Yeah, we are finishing. We wanna let you know that we are using ToxiProxy to simulate latency. It's very important to feel it like it's in a server. Also, we are using protobuf to the communication between applications, like the front-end clients or the web browser clients. Also, we have less than 3,000 lines in Elixir and less than 700 lines in Rust. We are using Rust to the collision detections, movement, and distance calculation because it's pretty fast to do that.
Yeah, one quick notation here is we thought about using it for some level of game representation, but we went away from that, and we are using nifs specifically for the math calculations. Most of those are like 1 line, 10 line math calculations, and without any context of the game, just collision detection, distances.
Just physics.
Yeah.
So that's it. Here you have a QR code. You have there our repo because it's an open source backend. Also our Twitter, webpage, and so on. So thank you.
Thank you for coming.
One more thing. we have 2 cell phones, so if anyone wanna try it, let's look for
meet us outside and you can play.
Yeah. Thanks.
All right.
Yeah.
I think we have time for one question. So, first hand I saw.
Hi guys, thank you for the presentation. That was awesome. I think everybody agrees here.
Thank you.
One of the questions that I was wondering, since you guys are using LiveView, of course you mentioned the netcode. Of course you mentioned that you're also using LiveView, that you're not sending diffs. I understand that. One of the problems that usually, you mentioned similar to PUBG or MOBA, right? But one of the problems that FPSs have usually is whenever somebody's speaking and rushing, usually that person has an advantage over ping. Of course, the protocol is different. Of course, you guys are using sockets. But do you believe that LiveView can maybe overpass that, maybe can solve that issue, that the problem with the state of the player that is rushing is usually ahead of the person that is receiving the data? I don't know if I made myself clear.
I think there's a lot to unpack. I mean, the first clarification I want to do is that we are not using LiveView. We are using the WebSockets on top of which LiveView usually work. Awesome, thank you. I'm not sure how we would use LiveView to solve that. Do you have an idea of where you're going?
Sorry, I just meant, I said LiveView, but I just meant the socket.
Yeah.
Sorry.
No, or sockets. Like, how would, I'm sorry that I'm answering a question with a question, but how do you think that WebSockets could help you solve the problem of rushers being in advantage?
The thing is that the problem usually happens because I'm sending the information and the server is still waiting to send for the other person, right?
Yeah.
basically speaking, of course, I'm not a pro here, but we're speaking in basic terms here. So maybe with that speed that you're saying, maybe you could find that sweet spot that you just mentioned. Maybe you could reduce that amount of ping that would almost be imperceptible in that case.
That's a very good question. I'm not sure. The shortest answer I would give is that I think that the good thing about this is both WebSockets, but also I think that the biggest bottleneck solver is actually the fact that we have a gen server and the fact that the sockets are separate processes. And I think that that will help more than the fact that we are using WebSockets. WebSockets are a very fast way of communicating, but I would say that almost every game probably has a way that they're not doing HTTP requests, of course. So I wouldn't think the bottleneck is in the communication layer. It's probably more in the concurrency architecture. So I wouldn't be confident in WebSockets solving that kind of problem. I would focus somewhere else. I'm sorry that the answer is not as specific, but that's where I would start looking if you're having any of that trouble. Thank you.
Thanks.